Here we are coming to one more area of titration reactions, so-called complex symmetric or simply EDTA titrations. So what stands for EDTA? It's ethylene. Ethylene is CH2CH2, diamine, two amino groups, tetraacetic, 1, 2, 3, 4 acetic acid groups. So ethylene diamine tetraacetic acid. What is special with this molecule? Uh, as you know, there are plenty of different complex compounds. They have very different stability, very different compositions. But the EDTA occupies very unusual position in this area. It makes stable compounds with most metal ions except of group number 1. Especially it makes stable compound with calcium. As a result, it can dissolve calcium carbonate or prevent calcium salt from forming. That's why it's very important when you deal with hard water, water that contains lots of magnesium and calcium ions, which can form insoluble compounds. Check your shampoo, you'll find EDTA in it. And this is why this compound is made in thousand tons quantity, is very inexpensive, and that's why it's very attractive as an analytical reagent. Now, from point of view of analytical chemistry, what happens? Let's look at one example. Simply metal ion complex, in this case it's manganese. And what does it form with the EDTA? You can see that you have 1, 2, 3, 4, 5, 6 atoms surrounding manganese into distorted octahedral fashion. These atoms are located from every side. There is no other molecule that can approach manganese. The most important is there is no chance the second EDTA molecule can react. So we have first very stable compound because so many atoms interact with same ion, and second, composition is always 1 to 1, one metal ion, one EDTA for minus an ion. That's fantastically convenient when you have only one possible reaction and coefficients are 1, which makes calculations even easier. Now, there are a couple of other compounds that have similar structure, but their use is far limited. Most of work is done by EDTA itself. Now let's look at acid-base properties. Here we have 1, 2, 3, 4, 5, 6 hydrogen atoms that can react with hydroxide and dissociate. So we have 6 pK values. First proton of carboxylic group goes at very acidic pH, essentially at 1 molar acid. The second still going very low pH, quickly followed by the third and fourth. So at pH around 3, 4 protons are dissociated. Now, if four protons are dissociated, you still have two of them left, so you have two minus an ion. After that, at px 6, one of nitrogen protons goes, and at pH 1037, the very last proton is going from nitrogen. Above this pH, the predominant form will be EDTA 4 minus, or in this notation, Y2 4 minus ion. So we are going from 4 minus to 2 plus with 6 protons. These calculations would be very difficult to make, but because of importance of this compound, people did lots of tools to simplify the calculations. So for example, this is a chart you can find practically in any reference book showing concentration of each of form 4 minus, H3 minus, H2 2 minus, H3 minus, H4 molecule, and then two cations as a function of pH. Here is fraction of each of form in log scale from 0, 100% to very small 10 to the negative 6. Alternatively, you can use tables for fraction of our most interesting 4 minus ion. You can see that at alkaline pH fraction is 1 or very close to 1. Then in very acidic pH, fraction is fantastically small. At pH 0, at 1 molar solution, out of 1 mole, it will be 2 or 3 molecules dissociated only. This table is useful if you need to do any calculations, because everything is calculated for you. Now, formation constants or stability constant of metal EDTA complexes, they are all very large. We're all talking about 10 power 20 or higher. The only small values are alkali metals, lithium, sodium, and potassium, and of course rubidium and cesium are even lower. Other 1 plus ions like thallium and silver also form relatively unstable complexes. All other compounds are very stable. 2 plus ions, 10 power 10 or 10 power 16, with copper 10 power 19. With 3 plus, we are easily coming into enormous number like 10 power 25. With 4 plus, it's 10 power 30. Very large numbers. But with 3 plus, you can find 10 power 40 as well. So fantastically stable compounds. And this compensates the small amount of ions we need for dissociation. So, because of pH behavior, we cannot use equilibrium constant directly. We use conditional constant. This would be equilibrium constant at some specific pH. Actually, biologists love equilibrium constants. So in this case, a stability constant will be complex, our product, metal ion, but instead of A4 minus, so active form, we put total concentration of EDTA. In this case, we can calculate our conditional constant from formation constant and a log of fraction of EDTA, where we are getting this number from the table on previous slide or similar tables in the reference book, where we are taking this number from a chart or table in another reference book. So this and this number are available. You just add them up. This number is of course always negative, and you have your conditional constant. Why you need conditional constant? Because it allows you to say if titration possible or not. In general, the rule is that you need conditional constant at around 7 or better 8 to have reasonably possible titration conditions. Again, log of conditional constants should be around 7 or 8. Then you have a jump in log of concentration of metal, and you can stop at some decent equivalent point. Of course, if stability constant is larger, your titration is easier. So this is conditional formation constant for strontium. Jump is still reasonable, but calcium is much better, much sharper jump. Sharper jump, easier is titration. The situation can be complicated if your metal ion forms compounds with your buffer you are using. For example, if you are using ammonium buffer, zinc ions form complex compound with ammonia, Zn, NH3 2+, and more ammonia you add, smaller is the jump. You can calculate conditional constant in this case as well. We seldom do that. Why we seldom do calculations like this? Because there are so many procedures already developed. So we mostly copy paste the conditions from titration. Now, to do titration, we need to have indicator. In this case, what do we want to indicate? We want to indicate metal ions. So our metal indicators will be compounds that change their color in presence of metal ion. For example, area chrome black tea is blue when it is free, and it's red when it forms a complex. Murixide is violet or blue when it's free in alkali solution, and it is yellow when it forms the complex. Xylenol orange is usually yellow in acidic solutions, and it's red when it forms the complex. For any metal we are interested in, there are plenty of procedures already written. You only need to find the proper procedure for your case. Each metal can be titrated with different indicators, and in this case, you can use different conditions. For example, you can see that nickel can be titrated from pH 3 all the way to pH 12. You just use different procedure for each of these. Uh, Indium can be titrated from very acidic solutions, pH 1, all the way to pH 10. Again, different indicators are in use. For some metal ions, you are more limited. You need to use only acidic solutions because otherwise they form insoluble precipitates. Anyway, with EDTA, you can determine practically any metal ion in periodic table except of the first group. That's fantastically convenient approach. You have one solution in your lab and you have a reagent that you can use to titrate any metal ion you may need. You prepare a solution of some metal ion salt. Usually it's approximate because you do not have 100% purity. And then you titrate with EDTA. After that, you know precise amount of metal in this solution and you can write the label with certified, very reliable concentration. Again, EDTA has multiple uses in industry and in biological, agricultural aspects other than analytical. Fantastically important molecule.